Okay, let's continue our understanding of probability and how it will play into our statistics class. The understanding of probability is the chances of the occurrence of the event happening in a percentage value. So now we're looking at more than one event rather than what we did in section 4.1. And special attention will be made to conditions that identify the process to take place. Again, make sure you're taking notes. Make sure you pause anytime you feel you need to hear it twice. So we're going to start with a compound event. Compound means more than one time. Oops, sorry. Our textbook says a compound event is any event combining two or more simple events. Simple is a key format because the more complicated the research on probability, the more profound the attention to detail is. And we're doing a survey course, so we're going to keep it as simple as possible. The addition rule has to do with two or more events that use the word or to distinguish each event. So, or means to add. So here we go. And we have two structures here. And for those of you that are not familiar with notations, you know, I've used the N of the event, which means the cardinal number. And then I have the N of the sample space, which is the total events possible. So these nomenclatures here imply cardinality, which means count. And look at things that overlap. Now, when this occurs, we have to subtract so we don't double count. And we use a symbol of and, probability of A and B, meaning that this is the shared elements and we subtract them. All right. So the probability formula tells us the probability of A or B equals the probability of A, the one action event. So we're going to say this is event 1, plus the probability of B, which is event 2, minus their shared elements. All right, now we don't have very many of those, so I'll be specific and you will recognize when that occurs. Now we need to look at particular sections of this to make sure. I'm going to make it larger so you can see. Is a summary of key points in the addition rule To find P of A or B, first associate the word with or with addition. And I've said that. This is the third time, which hopefully sticks in your brain. To find the value of P of A or B, add the number of ways A can occur and the number of ways B can occur. But be careful to add without double counting. Double counting. All right, so that's that intersection point. So now let's talk about disjoint events and the addition process. Disjoint, if I drew you a Venn diagram, would mean that we have event A and event B, and they share no elements. They're called disjoint. Kind of like a medical term, isn't it? To be dislocate something, you disjoint something. But anyway, disjoint means there's no overlapping. So they are said to be a very important word. And the word is the sets are independent. They stand on their own 2 feet, independent. That means that one action does not affect the other. So I'll give you an example. The probability of an ace from a deck of cards, or the probability of rolling 6 from one die. And that's not to kill yourself. One die is one, because you have a pair of dice. It's a die, and they have 6 sides. So this is what disjoint means. All right, so let's get to some examples. One of the ones we're going to start with is understanding what I've given you as information. And so we're reading for context. And you're going to see a lot of numbers, and sometimes we don't use them all. So you have to be very careful in probability. There are 15,958,866 adults in a region. So our population for a region is 15,958,866 adults. If a polling organization randomly selects, that's a very important, remember we said we prefer simple random sample, but randomly selects a quantity, then we have the idea of what is happening. So we have randomly selects 1,236 adults from the pool without replacement. So this is our N. It looks like I'm writing the whole thing down again, but what I'm doing is cataloging. Are selections independent or dependent? All right. Well, they are dependent, and that's the problem, because without replacement means that not every element gets to be chosen independently of the other. If you pull one out, then you've affected the remaining quantity. So is the selection independent or dependent? And I just spoke. They are dependent because we're using the same set. Not like the what I gave you before, a deck of cards and a dice. All right. Now it also continues on. If the selections are dependent, can you be treated as independent for the purpose of um, this item? Uh, well, the pool is affected by each of them. So can it be treated as independent? Well, there is a rule of large numbers. And I think 15 million qualifies as a large number, so that you can treat selection as independent so long it follows the 5% rule. And that is the sample is less than 5% of the original, which in this case it is. So that gives you an idea. It's a complexity of statistics within the generality of statistics. All right. So we're going to talk about another aspect. Now, we haven't done any real problems yet. We're just getting used to definitions. This one is a complementary events and the addition rule. Complementary events are the not of it. And we have, okay, so if I have the probability of event A, its complement, mean all elements not in set A is the probability of A with a bar on top. This bar implies complementary, and it's not like free. All right. Now, what we do know is that if I do 1 minus the probability of A, I end up with the probability of A naught. Because if I add the probability of A plus the probability of, A naught, I get 1 or 100% of all of the probability involved in this exercise. So we're going to have an example on complement. All right. When a man observed a sobriety checkpoint conducted by the police department, he saw 671 drivers were screened and 5 were arrested. or drunk driving, or driving under the influence. Based on those results, can you estimate that, oh, we can estimate that the probability of drinking while intoxicated is a very small probability. Probability of W, and that means that it is intoxication. So we have this probability. Uh, Now it says, and getting someone who is intoxicating. What does PW bar mean? It means the complement of that probability. So this means people who uh, were not driving while intoxicated. All right. So how do we figure this out? Well, we said that if I wanted the complement of a set, I do one, which represents 100% of the probability, minus the probability of the drunk drivers, or drivers that are intoxicated. Close the door. All right. So I can give you this value because I have this value here. So I'm going to do a little bit math. And that gives me not driving intoxicated. And that would give me an arithmetic value of, and I would have 99255. Simple math. Okay, now understand I'm doing this for educational purposes. So I'm showing every step. But if you can follow along, this will make sense. So here we have a table of items, and we're talking independent events. All right. Use the following table, which lists drive-through order accuracies at a popular fast food chains A, B, C, and D. Assume that the orders are randomly selected from those included in the table. Well, we must find the cardinality of all the orders. So that means that I'm going to have to add and find the total. So I'm going to use my calculator. And I'm going to add across and see what I get. 330, 277, 243, 131. And I hit enter and I get 9. Let me look at it. 330, 277, 243, 131. You know how sometimes I get a wrong sum. And then those are orders that are accurate. Total orders that are accurate are that number. Double verifying. 36 and 51 and 39 and 19 were orders that are not accurate, the complement of it. And so if I add both of them together, I'm going to get 1126. All right. So I have this situation here where I have the 1126. And now I'm going to see what they want us to figure out. If one order is selected, find the probability is a capital P, of getting an order from restaurant A or an order from that is accurate. So these are two considerations. So two items. And let's see what we have. Restaurant A or, okay, that means that addition process, or accurate. All right, now let's look at that. So if I wanted restaurant A, that would be these two numbers here. And I'd add them. And I would get 366. Okay? Then there, 666. Okay. And then if I wanted accurate orders, I would have this bar here, which is 981. And we notice that we have what we call an overlapping. So we're going to have to do that minus item at the end. So let's see what we have. All of them are under the total quantity. So let's structure what we know. I'm going to shorten it to A, or probability of AC, accurate orders, minus the probability of A and B. Okay, so now that we have our order of what we're going to do, we're going to construct what we have. The probability of restaurant A was 366 over that 1126 plus, because it's an or. And then we have the 981, which are all accurate orders, over the 1126, minus their overlapping of 330 over that 1126. All right. So now that we have that, we can use our calculator and do the math. I'm going to move it over here, and I'm going to clear everything. And I'm going to do my numerators. 366 minus the 981. I'm sorry, plus. Oh, what am I? Way ahead of myself on that. I can always move the arrow over, and then I'm going to do the minus 330. My brain is working too fast. Over the 1126. All right. Well, we want the probability. So we need a decimal or a percent, whatever the problem asks for. But in this case, we want a decimal. So we're going to take that number and divide by the 1126. And we're going to get an irrational decimal value. We usually do about 4 decimals if we have small, or 3 if we have large. In this case, we're just going to do 4, just to make on the safe side, using proper rounding rules. So the probability of getting restaurant A or accurate orders, which were the largest of the considerations, is almost 90% chance of selecting one that was accurate or restaurant A. So here we have one on dependent or independent. And so we're going to look again at a data. It's similar to the one we had, different numbers. And again, this is for instructional purpose. And it's on the popular food chains A, B, C, and D. And they're drive-throughs, which is usually where all the accidents happen on inaccurate orders. Assume the orders are randomly selected from those included in the table. So what's our first step? Well, we find the total orders. So that means we're going to add, and I'm going to add, again, I'll add horizontally. Oh, added to 2, 6, 4, added to 3. I'm sorry, that's a 2. 2, 3, 4, added to the 1, 3, 5. And I'm going to double check 320, 264, 234, 135. Okay, so I'm going to get a total of 953 that are accurate. Now I'm going to add the row that is not accurate. So that's 38 added to the 51, added to the 35, added to 13. And I'm double checking, so sometimes it gets sensitive. And I make mistakes. So this is 1090, it looks like. All right, so now that we know the total that is in our data set, it says the A section says, assume that the selections are made with replacement. That makes it independent because the pool is always the same. All right, so they're always the same, so we're independent. And 2 orders are selected. Find the probability are both from restaurant D. All right, and we already determined it was independent because it's with replacement. Another, the first selection is taken and logged, and then it's done again. So in this case, we understand we need the sum of D, restaurant D. So here is our restaurant D, and we're going to add them. It looks like 148. So we want the probability of restaurant D. They're all made with replacement, or probability of restaurant D. So we are looking at 148 were the number of orders counted on restaurant D out of the 1090. And we take the second one and we're going to put the 148 on the 1090, and we're going to get 296 out of the 1090. All right, but this is an advanced one on, this is not an or, this is both, this and this. These are 2 requirements, so it's not an or. This is a wrong premise for me to do, and that's because I have it out of place, and I thought it was another or, and I apologize for that. So what I'm going to do is I'm going to erase this part here, and we know it's independent, so that part is correct. But we're talking about and. two wanted outcomes, and this and that. So and means to multiply. It is a multiplication rule. And I haven't talked about it. So let me talk about it first and come back to this problem. Just where I left it, and I'm sorry. It's right here. Somehow I got them out of order. What can I tell you? This is a multiplication rule when the probability requested uses the word and to describe two events, two or more, that are inclusive, or should say restrictive. By the structure. All right. So it's called the notation, the multiplication rule. The notation for multiplication is the probability of event A and event B. And that would give us probability of A times probability of B. So that condition is one of the ones that give us pause. And the one we have up front that I was forcing it to be an addition because I thought that's what I had was not a criteria. Again, we have the inclusion of independent events. When the sets are disjoint or are with replacement. And this affords us an equal chance of being selected again. That makes it independent because, as I mentioned on the problem I started and didn't complete, dependent events are when a single set of elements or population or sample space is used and the selection is not returned to sample space. And what this does, this means the cardinality of the event for the next selection is -1, as is the cardinality of the sample space. Because a pool is reduced in quantity. That's why it's dependent. Because we make an assumption that we're selecting the one we desire. And I'll go into that as we get further in the lesson. So let's go back up here. So this is the probability of restaurant D and probability of restaurant D. But this is with independence. So in this case, I'm going to have the restaurant D was 148 over the 1090 times the 148 of the 1090. All right, so here we go. And I didn't intend to make that mistake. I caught it and I forced it and I went, no, that'll be wrong. So here we go. I apologize. Let me clear my screen. We got some big numbers. 148 times 148, and we've got 21,904 divided by the 1090 times the 1090. And we have a giant number, 1188, 100. Okay, so now we're going to do the math on it. So let's see what we can get. 21,904, making sure I didn't mess up. Nope, I didn't. Divided by the 1188, 100. 1188, 100. 21,000. Okay, we're good. And we get this probability. Okay, it is a small amount, but we're going to go to 4 decimal places. And we're going to do the appropriate rounding. And this is our probability that both with replacement are this value. So let's look at the B question of this problem. And the B asks, assume that the selections are made without replacement. Now they are dependent events. And I can demonstrate what that implies. So we're still looking at the probability of both from restaurant D. Right. So on our first draw, we assume we have the 148 out of the 1090. And then on the second draw, we assume we took one of the ones we were looking for from restaurant D. So that leaves us 147 out of 1089. Now you can see the small variation in what we're going to achieve here with this second problem that is dependent. So let me do the math. And it's slight because the numbers are so large. And just on that portion of the ratio that we got, it is slight. So, and like we're proving the fact that when you have large numbers, you can consider them independent because it's slight. One one eight seven oh 10. Okay. So we're going to do those 4 decimal places, and you can see that it is a slight difference, but not enough if we had rounded to say 3 decimal places. So what this does is show you the connection of large numbers and independence. So now we're moving forward. This is that treatment of large numbers, and that is treating dependent events as independent is a 5% guideline for cumbersome calculations. So when sampling without replacement, the sample size is no more than 5% of the size of the population, treat the selection as being independent, even though they are actually dependent. And we proved that with the example above. So we've done that, and let's see what else we have. Here is a multiplication rule and condition. The principle of redundancy is used when system reliability is improved through redundant or backup components. Assume that a student's alarm clock has a 16 and 2% daily failure rate. And I put it as a decimal. What is the probability that the student's alarm clock will not work on the morning of an important exam? Okay, well, the probability, of course, is 162, decimal 162. That's all it is, because we only have the one. It is one possibility, and it's the probability of one. If the student has two such alarm clocks, what is the probability that they both fail on the morning of the important exam? Well, this means the probability, alarm one, oops, I can't spell. You noticed that already. And alarm two, failure. All right. So we're saying, okay, what's going to happen if both of them fail? Both. All right. So we want the probability of alarm one failing times the probability of the alarm two failing. So we know what we've got. We know the probability of the alarms now working is decimal 162. And redundancy means that the more we have of them, the likelihood of one of them working, right? So let's do the math, and we're going to do it to 5 decimal places. So let me clear my screen, pull it up a little bit. So I have the decimal 162 times the decimal 162, making sure I do the entries correctly. Garbage in, garbage out. All right. So I have this value, and we want 5 decimals. 1, 2, 3, 4, 5. So we have approximately that possibility. Well, that comes to be like 3% chance of both of them not working, which makes sense if you think about it. Okay, what is the probability of not being awakened if the student uses 3 independent alarms? So now we have 3 of them. I want to always forget the L. Sorry about that. Okay, well, each one of the chances of it failing are, of course, 1.162. And those of you that are very smart in math will use an exponent to get the value. So whatever you want to do with your math is okay with me. And I would have done that myself. But I'm showing the events, each one having its own due value. Okay, so I have them all correct. And I have, oh, I got the answer and didn't write it down. Okay, we want 5 decimals. So we're talking about approximately 4/10% of all of them not working. Very, very slight. So that tells you how this probability does work. So let's see what they're assessing. Do the second and third alarm results greatly improved reliability? Oh, yes. From 16.2% to, with the 2 alarms, 2.6% to 0.4%. So this is so slight that they're not going to have any problems. All right, and this finishes a section. This was a problem I omitted, but I have it listed. But I am going to go to the last one. And I forgot to erase the other 2 items. A statistic class consists of 5 males and 7 females. 2 of those students are randomly selected without replacement. What is the probability that both selected students are females? All right, now we know that these are dependent because they're without replacement. So we have to find the total. The total is 12. And the cardinality of our event is 7 females. So we're going to have 7 out of 12 for the first one and 6 out of 11 on the second one. So that gives us 7/12 times the 6/11, and I get a 42 over. Oh, that's a little bit more than I can do in my head. 132. And in a decimal percentage rate, we're going to have the 42 divided by the 132. This is a repeating decimal, so we'll do 3 decimal places. It's about 32% if we were doing a roundabout. We have done all of section of 4.2 on addition and multiplication of probabilities. Now, please do your homework and let me hear from you if there's any issues. I am sorry about that one conditional one that I accidentally tried to force it, but I caught it, so we're good. Thank you very much. Be sure you read the problems correctly, not like your instructor.